Sure.
Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RPCCPS IISc. Today's talk is by Professor Harsha, and he will be speaking on towards a theory of exploration in continuous time reinforcement learning. Professor Harsha is an assistant professor in associate. Very simple.
Okay.
Professor Harsha is an associate professor in the School of Industrial Engineering at Purdue University and a J. Tinsley Oden visiting faculty fellow at the Oden Institute at the University of Texas at Austin. His research interest as an applied probabilist encompasses stochastic modeling, optimization and control with applications to machine learning, simulation and statistical inference. His research is supported by National Science Foundation, including NSF Career Award and the Purdue Research Foundation. He is an editorial board member at Operations Research and Operations Research Letters and Queuing Systems Journals. Before we move on to the talk, we request everyone to subscribe to our Google group for more information on future talks. You can also visit our website for more details from the chat box. Please to check. Finally, we request the online audience to keep your microphones on silent during the duration of the talk. Only when asking questions, please unmute yourself and ask directly or post in the chat box so that we can relay them. Over to you, Professor.
Thank you. So I'd like to thank Parimal for the kind invitation to come talk here. And so I thought I'd fit. I think I fit within the intelligence part of CNN. So I'm going to talk about some work that I've been doing, I've been thinking about a lot on continuous time reinforcement. And in particular, sort of stepping away from the usual assumptions that underlie reinforcement learning models, in particular Markovian. And the word towards is doing a lot of lifting because this is really a talk on control, but it has a lot of implications for reinforcement. So we're headed in that. I should point out that this is a joint work with my former student Prakash Chakraborty, who is currently at Penn State, and my colleague Sami Tinda, who is at Purdue. And this is supported by NSF. Okay, so here's a sort of broad outline of the talk. I'm going to start with a reasonable amount of motivation. This is convince you that, okay, we should be thinking about problems in continuous time. There are interesting questions here. Then I will, sort of segue into talking about some classical stochastic control and its relationship with R. And then what we are doing in pathwise rough control. And this is based on a paper that's in preparation with Prakash and Sam. So if you ping me next week, hopefully it's on archive, or I can share it with you. Okay. So let's start with the motivation. And you've all probably encountered this diagram. It's from Sutton and Bartle, classic book on reinforcement learning. And the setting in reinforcement learning is I have an environment that's unknown, and I have an agent who takes actions and interacts with the environment. And in return, the environment provides feedback in the form of state information and reward information. Okay, and typically we will assume, in the reinforcement learning literature, that this environment has Markovian dynamics. In the sense that the state of the environment conditional on the current state and the current action taken by the agent, follows a certain probability distribution. It only depends on the current state. And the goal in reinforcement learning is to learn to take good actions or optimal actions in an efficient way. Actually, you want to learn efficiently. And you want to do this by balancing exploration of the state and reward spaces. So you don't know anything about the environment and you're trying to learn as you go along. But you also want to exploit whatever information you collect, what you've learned so far. So there's this balancing problem between exploration and exploitation. Okay, and this is sort of at the heart or the core of reinforcement learning. And a key question that arises when you think about this problem of reinforcement learning is what is a good strategy for exploring the state action rewards? What kind of strategy can you use that lets you sort of explore in an efficient? Well, one strategy that's quite commonly used and it's quite popular, both from a heuristic perspective and also from an optimality perspective, is using a Gibbs or Boltzmann or softmax control for exploration. Right? So this involves using a conditional probability distribution on the action phase, conditional on the current state. Okay, so given the current state, you choose the action according to this probability distribution that has this Gibbs form. Tau is some kind of a hyperparameter that you should think of as a temperature parameter. So if tau is close to 0, this thing behaves like an argmax. On the other hand, if tau is out towards infinity, then it's more like a uniform. And Q of SA is some kind of an assessment of the value of being in state S and taking action. So this is a widely used control strategy for exploration. In fact, it can be shown that these are sort of nice in some sense. In particular, if you change the learning objective a little, so you introduce like an entropy term into the learning objective, and towards the end of the talk, I'll make this a little bit clearer. You can actually show that the is actually a Gibbs type distribution. Okay. So the optimal control and one that actually balances high reward, which means that you're doing like good exploitation with maximal randomness, which lets you explore efficiently. Okay, so that turns out to be of Gibbs type. Now the question is, all of this that I've told you so far is in discrete time. Okay, there's extensive understanding of exploration strategies, particularly these Gibbs type control strategies in discrete time. But what can we say in continuous time? In particular, what can we say when it's like a high frequency system? Like when you're interacting with this environment repeatedly at an incredibly fast clip. And also, what can we say when the environment is not Markovian? It has like correlations that is beyond the Markovian correlations. And to convince you that these are important questions, let me just briefly give two sort of motivating problems. One is from high frequency trading, where the goal in high frequency trading is typically to learn policies to optimally execute buy and sell actions. And one example would be limit order book. So you see like this. So, yeah, so in a limit order book, you sort of have like two, it's like a double-ended queue. So you have buy orders that are in queues here at different price levels. Okay, so this is the amount that someone with wanting to buy like an asset, be a stock or an option, is willing to pay. And on the sell side, these are the prices at which different market participants are willing to sell their asset. And the goal, of course, is to sort of settle this market. Right? And the way you do that is to look at what's called as a spread, and then you settle the. So like that's one sort of compromise solution. From the perspective of like a high frequency trader, you want to know how to optimally execute large buy and sell decisions. Because if you at one shot, execute a large buy or sell decision, you can actually change the market. And there is advantage in just being a market taker rather than a market maker. And if you then decide, okay, I'm going to break up this large order into small chunks, then you're subject to market risk because the longer it takes you to sell these things that you have or buy things that you want, the more liable you are to market risk. So there is like an optimality question. Okay, so learning how to learning these policies from looking at trading data is an important problem. And again, this is like a high frequency setting where these decisions are being made, thousands of times, even higher. Another example would be in high-speed communications networks, where you want to learn policies to switch inputs to outputs, for instance, at high speed. And again, this is a situation where you need to learn how to do this kind of switching when the environment is non-Markovian. So if the environment is Markovian, we know a lot. But if the environment is non-Markovian, it turns out that you probably want to use reinforcement to find a good policy. And also in high frequency trading, if your trading decisions are sort of premised on volatility, volatility actually has sort of Markovian structure, non-Markovian structure. So again, you want to learn how to make these types of decisions in a non-Markovian. Okay. So high frequency and non-Markovianity, naturally pop up in these types of systems. And our objective, in the long run with this project, is to understand how to learn these things. But for now, we're going to focus on, how do you do exploration?
I want to question. I know it's not but how does this high frequency trading go? I didn't understand the bid price. So I thought some people are bid, right? And some people are willing to sell. Don't you just match or what do you do?
Yeah, so one simple way to settle the market is you take the lowest sell price and you take the highest bid price. Right? Typically there's a spread between. Okay, so they're not necessarily going to coincide. So one way to sort of settle the market is to say, okay, here's a mid price, and then you force people to settle that.
So mid price is what? Between difference between them?
Yeah, like you're looking at the spread, and then you're saying like half.
Okay, and that's one the both will be okay with this. That you have to
force them to accept.
So it means that you have to pay a little bit more than what you need to pay, and you have to sell.
Exactly. Yeah. And then the hope is that in the long run, if you participate in this market enough, at some point you will flip roles.
And you have this different, different height stuff, right? Is that different goods at which you're selling? Or?
No, those are the numbers. Yeah, it's a good, actually, point. So these are the numbers of people who are willing to, for instance, sell at this price.
I see. So the lowest one is what you took them in from.
Exactly. Okay. Yeah. Because if you're selling, you want to sell at the highest price. So right. This is only an example, right? So it's more likely that you will see, larger numbers of bidders.
And this is what is done in high-frequency trading.
Quite often. So this is called as a limit model.
Who decides this? Is the stock exchange?
So there are exchanges that run. So this is called as a limit model, and there are exchanges that run a limit model.
I see. So exchange would have its own.
That's right.
Formula of how they trade.
Yeah. In fact, these are all like double-ended queues. So there's a lot of queuing theory that's going on inside of all of these. Okay. All right. So let me start, the technical part of this talk by first, recalling for us classical optimal control. So this is a setting where there's no stochasticity in the dynamics. I'm going to assume that the state of my system, which I will represent as XUT, follows this ordinary differential equation that's controlled through this control function UT. So UT is in some set U, and it's the control that's chosen by the controller at time t, and there's some initial state. Okay. Now the objective in optimal control is to maximize or minimize. In this talk, since we want to connect with reinforcement learning, I'm going to use maximization and reward instead of cost. So we want to maximize this objective over all possible control functions U. And the objective consists of two parts. One is like a running cost, and there's a fixed time horizon capital T, and I have a terminal cost G. And under certain conditions on this running reward and the terminal reward, it can be shown that the optimal value, one that maximizes over U, is going to be the unique solution of the so-called Hamilton-Jacobi-Bellman equation as it's done. So this is all well known. The
Sorry, one question. You could have done an infinite horizon counterpart for this as well, right?
Which
one like you.
Yeah, you can actually write down a discounted infinite horizon cost problem.
Even average, right? 1 by t.
You can do 1 by t like an average cost. Though that may be less interesting. Classical.
Why?
I think you need some kind of logicity to make that meaning.
What is this terminal reward? Can you please explain?
So think of it as, at the end of the time horizon, I want to do, for instance, begin a particular state. So if I'm in that state, I get a high reward, like let's say plus infinity. If I'm not in that state, I get a very low reward, let's say negative, for instance. So I want to make sure that I end up in some nice state. All right, so this is the control perspective. Now, if I turn to reinforcement learning for these types of dynamical systems, there has been a fair amount of work, actually, not a lot, but there's been work over a reasonable amount of time. Like I think this paper here, this paper by Kenji Doya, and I think that's from 1990 or maybe a little bit earlier. So people have been thinking about reinforcement learning for these types of dynamical systems for a while, and the RL approach usually uses the RL approach is to use paths XU, right? So you can only observe the solution of an equation like this, and you want to use these paths to estimate the optimal value function V star and an optimal control. And in this paper, Doya actually introduces an active critic type algorithm that uses temporal difference learning for policy evaluation and policy gradients for policy. Okay. So in reinforcement learning, practically all methods are in one way or the other implementing something called as policy iteration. Okay. We are sort of going through repeatedly, evaluating a given policy and then trying to improve that policy, and then evaluating the improved policy and then improving that policy until you actually converge to the optimal. And under very general conditions, it can be shown that policy iteration actually converges to an optimal policy. So all of RL is in some sense implementing this. Now the question is, how do we extend these types of reinforcement learning methods to stochastic dynamics settings? Well, there's one approach that one can take, which is to just introduce a stochastic term into our equation. Right, so I'm going to introduce this Brownian term. Here, WT is Brownian motion, and I have some diffusion coefficient. And this will turn our problem into one of learning over a stochastic dynamical system. And my objective now has to change. I will have to introduce an expectation. For instance, I have to take care of the stochasticity in the problem. I want to resolve the uncertainty that's coming from the fact that this is a stochastic dynamical system. And I'm going to introduce an expectation into my objective.
So just one more question. Yes. So far, it still looks like it's Markovian, right? Because the evolution of XT only depends on the previous current XT, and then this.
That's right.
You have not still gone to non-Markovian.
Not at all. Yeah. So this, if you were thinking about taking the optimal control perspective from a dynamical system to a stochastic dynamical system, the main question is, what is the stochasticity that you're going to use? The natural choice is a Brownian motion. So, and I would say this is like step number on that. And you're right. Here nothing is non-Markovian because it depends on the control at this point in time, and the driving noise is also Markovian. So again, in the reinforcement learning setting, when you don't know the underlying model, you can use what's called as model-based reinforcement learning, where you learn the underlying and then use it in learning an optimal value or optimal policy. Okay. So in order to do that in this RL setting, you want to use the control that you're imposing. Again, to both explore and explore. Okay. And you want to use it to interact with the unknown environment. So that's the whole exploration part. And then you want to choose a good action that lets you exploit what you learn. Unfortunately, the controls that we assumed so far, coming from the dynamical systems perspective to the stochastic dynamical systems perspective, I never changed the controls. These controls are still like function, deterministic function, and those don't actually facilitate any kind of exploration at all. Okay. So, and another problem, of course, as we just discussed, is not all stochastic systems are going to be driven by Brownian motion, and we want to somehow relax these two conditions or generalize these two conditions. We want to move away from these deterministic controls to controls that actually facilitate exploration. And we want to look at stochastic systems that are driven by something other than Brownian motion. And when I say something other than Brownian motion, I mean something that is non-Markovian. So the first generalization that I'm going to talk about is one on relaxed controls. So this is how I'm going to introduce exploration into these dynamics. So remember, the previous equations that we had were this form, and in order to change these dynamics, I'm going to introduce what I will call as an exploratory state dynamic. So instead of the control ut, remember the control function was just a deterministic function of time. I'm now going to replace it by a function that takes values in a probability space. Okay. So let that sink in for a moment. So it's going to be a function of time, and this function of time, function in time takes values in the space of probability measures on my control space.
So gamma is measure value process.
So it's a measure, you can think of it as a measure value function, but it's not a process. It's not necessarily. So I think it's better to think of this as a curve in the space of probability measures on it. Okay, so given this relaxed control, I'm going to introduce it into the dynamics by changing the drift. And this is, for the purposes of this talk, I think this is the simplest way in which you can introduce these types of exploratory dynamics into the equation.
So you're linking the randomized policy with exploration sound.
Can you say that again?
You're linking randomized policy with exploration sound, right?
Yes.
But with deterministic policy also you can
Well, not with these types of policies. Right? If I just say that it's a fixed some function of time, it's not going to facilitate any kind of exploration in the stochastic setting.
for example,
If that ut is, even if it is adapted, right, it's not necessarily the best policy to explore. So what I really want in some sense is, if I'm in a particular state, for instance, maybe I want to use either the fact that I'm in a particular state right now and then randomize over magnitude, or I use all of the history of what I've seen and then I randomize magnitude. But in any case, I think what I really want is to randomize magnitude. So this is the natural region.
This gamma which you have, I think it's what is hidden is that probably this gamma depends on the past of xt and x until t, right? Or not.
So in this version of the talk and the paper that we've done so far, gamma is not assumed to be adaptive. So gamma is just a deterministic function of time, but it is a probability on taking values and problems.
So you just pick some function of time which has different properties at every time, and there should be one.
Yeah.
But ideally, you would think like in what you see in this control, right? Every keyword that your u is a function of x.
Yes.
X keyword.
Yeah.
You say that's not good.
No, I'm not saying that it's not good. No. So let me be absolutely clear. This is probably not as good as an adaptive control.
Okay, you're saying if gamma was function of x, you do better.
For sure. Yeah. But in order to actually get the equations that we want, we didn't even have equations in this case. So gamma is just a function of time, but it's taking values in space probably. So I would say that this is like version 1 of the LIP. That's a good point.
So just going back to your first version.
Yeah.
Without the noise, you say that ut is a deterministic function.
Yes.
But with the noise, it should be a function of the state, but you're not permitting that.
It could be a function of this, but the way that I'm presenting it here, I'm sort of saying that it's not. It could be. Okay, so the second generalization that we want to do, as I mentioned, is to a rough environment. Right? So just briefly going back to this whole limit order book setting, the dynamics of of this type of system, particularly if you care about volatility in a stock market, that turns out to be like fractional Brownian motion. So it's not like Brownian motion. So you have to make decisions to buy and sell assets in an environment that is actually not Brownian. So we want to generalize in some way. And fractional Brownian motion is in some sense like the natural first generalization that you would try. Right? So just going back for a second to the model that we had, we have assumed that this process xt here is driven by Brownian motion. And as I said, in reality, some observations are not going to be Brownian, right? So in other words, these xt's, the states themselves are going to have, they're going to be more irregular than Brownian motion, or maybe less irregular, but not like Brownian motion, essentially. And another way of stating that is to say that the polar regularity, continuity of these paths may be different. So the paths of these xt processes, they might be different from the regularity that's associated with Brownian motion. And this sort of naturally leads to like a non-Markovian environment. And the first sort of generalization that I would think of in this type of setting is like a fractional Brownian motion. So if you don't know what a fractional Brownian motion is, don't worry. Essentially, it's like Brownian motion, but with a different correlation structure, autocorrelation structure. And it all comes down to this exponent h. So you should think of this as the Holder regularity exponent of fractional Brownian motion. Let me give you some simulations to sort of fix the ideas of what it means for h to change. Okay, when h equals 0.5, right, so this is actually Brownian motion. Okay, so h equal to 0.5 is Brownian motion. H equal to 0.7, so h is going to vary between 0 and 1. When h is 0.7, so you're getting closer to 1. Look at the path. Okay, so the path it's less jagged compared to Brownian motion. Okay, so what does that mean? It means that you have more correlation from increment to time increment to time. Okay, so the stochastic process has a lot of correlation when you go, from one interval to another non-overlap. On the other hand, when h is 0.3, right, so less than a half, the path suddenly becomes like this really jagged sample path. Okay, so what does that mean? So it just means that when I'm looking at the correlation between the increments of the process on one time interval and then another non-overlapping time interval, there is very little correlation. It can move almost arbitrarily. Okay, so fractional Brownian motions lets you span. Lets you span like all of these different sample path behaviors. Okay, and our proposal now is to replace Brownian motion with fractional Brownian motion. It's same sort of exploratory dynamics in the drift, just replace Brownian motion by fractional Brownian motion. So we're including Brownian motion, but also expanding the class of processes that we're looking at. Okay, so does that make sense?
How do you write DBT in terms of DWT and H?
So I'm not sure what.
So, like, many of this SE you can write in terms of generated by Brownian motion.
Okay. You're preempting the next. So let's move that. So the main step that we need to do right now is to solve this equation. Because we want to know what the state process is. So we have to solve this equation to get the state process. So we have to define, in other words, integrals of this form. We need to know what integrals of this form look like. So this is the crux of your question. Well, here are some basic facts about fractional Brownian motion. First of all, unless h equals a half, if h equals a half, then some of these things are true. B is not a finite variation process. Okay. Secondly, B is not a Markov process. If h is not equal to a half, B is not a Markov process. Okay. And if h is not equal to a half, B is not a Markovian. Now, this is the problem because Ito's theory does not apply to fractional Brownian motion. So all of that, exactly what you said, like, I want to define it as a solution of an SVE. The state of my process doesn't work. So you need another integration theory to make all of this work. And that is, what we're going to explore a little bit today on rough paths. Okay, so rough paths are a way to talk about integration for equations that involve driving signals like fractional Brownian motion, but it is a much more general. It encompasses fractional Brownian motion and etocalculus in a very general. So I'll give you a sort of very brief introduction to rough path theory. That is a whole lecture series on its own, frankly, and obviously can't do it today. But just enough to get us through this talk. And in order for us to talk about this integration theory for fractional Brownian motions, we will have to rely on the regularity of the sample paths and the Gaussianity of the fractional Brownian motion if we say that our driving signal is fractional. But rough path theory lets us look beyond this fraction.
I have one question. Is that if H is not half, will the Gaussianity be maintained?
Yes, I should have mentioned that. Fractional Brownian motion is a Gaussian process. Yeah, good question. Okay, so
is there an axiomatic definition of fractional Brownian motion?
like a Levy type construction.
Exactly.
I believe that is, yeah. Okay, so here's a brief summary of where we are. So we have this relaxed control viewpoint on exploration. So I've introduced this, remember this curve in the space of probability measures and controls. And that's going to be our exploration process, let's say. We have a rough environment, possibly fractional Brownian motion driven. Okay, it could be something else as well. But we want something that gives us non-Markovian dynamics. And for now, I'm going to focus on what I would call as pathwise. This will become clear when I present it. So I'm not going to be looking at the objective with an expectation. Okay. And towards the end, I'll explain why this is a hard problem in this non-Markovian setting. But for now, let's just focus on this pathwise optimization. And so here's a few prior works that are very recent and sort of focused on similar type questions. But none of them looked at this relaxed control setting. And there's also classic works on pathwise optimization. I highly recommend the paper by Leons and Souvenides. But let me move on from this and just briefly present our general framework for exploration in these non-Markovian type settings. So we have this equation just almost as before, and rather than being driven by fractional Brownian motion, I'm going to say it's driven by some rough path quote unquote zeta. Okay. Now this rough path will have polar regularity alpha greater than a third. Just to remind you, the Holder regularity coefficient looks something like this. For a path X, it's going to look at this. So soup over S T X S minus X T divided by T minus S. So it's this number. So I'm going to look at paths whose Holder regularity coefficient is larger than a third. And this can be generalized with some effort.
So you put alpha in the denominator T minus, that alpha is what?
That's
1/5, right?
yes.
But then soup will give you a number. You just say that such alpha will become finite, or what is the definition?
Okay, maybe I said something incorrect. So when I say Holder regularity coefficient, I mean this alpha. I don't actually mean this.
But then how do you define? You put any alpha and get some number, right?
Yeah.
So what is the definition for regularity?
So I'm saying that this path,
you put some alpha and you get.
I think I see what I'm saying. I think I should use something else. Yeah, let's say that it's gamma, okay, and this coefficient is going to be greater than. Okay, so the control space is going to consist of paths, which unfortunately in the stock is these are called as gamma. So these are going to be paths that are indexed by time, and they take values in this space of probability measures on the control space. P2 just means that you have at least two moments. And I'm also going to assume that in this control space, the distance between any two of these probability measures on a given curve satisfies this older inequality. So in the Wasserstein distance. So in other words, if I'm moving along this curve of probability measures, let's say something abstractly like this, and I'm looking at these two probability measures, then the Wasserstein distance between gamma r and gamma t is at most bounded by this L times this quantity here, with epsilon being positive. So in other words, as I'm going along this curve, I can't rapidly or arbitrarily change how quickly these probability measures will change. Okay, the objective that I'm going to look at is this pathwise. Notice that I'm not saying that there's any expectation. Okay, so this is the pathwise objective, and I'm going to optimize over that state path, xt gamma over there. And what I'm interested in finding is, first of all, the optimizer, and also what is the optimal value of this pathwise optimization. Okay. So essentially, I have this rough path driving this system, and I have an exploratory process. Okay. And I want to find what is the optimal exploratory process and the optimal value associated with this exploratory process. So this is the framework. Before I continue, are there any questions? Okay. All right, so result 1 shows that there actually exists an optimal control, relaxed control, under the assumption that the space, these paths, these curves of probability measures take values in a compact set, and the cost functions f and g are bounded, continuous in x, and lipschitz in gamma. So under these sort of standard assumptions, the supremum is achieved by some optimal gamma star in the space nu fc. So this is sort of unsurprising under these assumptions. This is a very standard result. The second result is more interesting.
One question. You have random evolution, right?
Yes.
And still sort of you're trying to maximize that random number itself, right?
Yeah. So here, so the way to think about this problem is I sampled a path. Okay, so I sort of resolved the path, and then I'm trying to optimize the path. So for each path, there will be a different problem.
So this gamma is a path dependent.
Oh, absolutely. We'll see an example where you can sort of explicitly calculate what the optimal gamma is. And it very clearly depends on this driving signal in an explicit way. Okay. So the second result is the derivation of the Hamilton-Jacobi-Bellman equation for this setting. And this sort of follows from the dynamic programming. And given the form of our problem, it's unsurprising that we can write down this equation that shows that the value function is sort of the fixed point of this equation. In other words, you can show, assuming that V is an element of C1. So this is an important assumption, that the value function, in other words, the solution of this, the fixed point of this equation, if you assume that it is C1, so there's at least one derivative in space, then it will be the solution of this Hamilton-Jacobi-Bellman equation, this PDE. Okay. I just want to point out a couple of things about this PDE. First of all, this function h is the so-called Hamiltonian. This will be important later on when we try to derive the optimal control. And also notice that we have this extra term. Okay, so in fact, I had written down the HJB in the ordinary differential equation. So there we have something like this. It looked like H of T, Y, U, and nabla b equals 0. Okay, so this equation actually generalizes the HJB for the ordinary differential equation setting, the dynamical system setting, by first of all, maximizing over the exploratory policies, and also we have this rough part of this equation. Okay, so there's a rough component to this equation. And this actually complicates the solution of the HJB equation further considered. And we'll come back to that in a minute. In fact, in order to talk about the solution of this equation, I need to take a detour, okay, for a few minutes and talk about what it means to integrate equations that involve rough components like this. Okay, so let's take a brief detour into the rough path problem. So far, I have not told you what a rough path is or what the rough path problem really is. Okay? And this sort of lies at the crux of what we're trying to solve. So the main integration problem that we run into in order to solve this HJB equation is resolving integrals that involve terms like this. In other words, you have to give meaning to an integral that looks like this, where this x is either fractional Brownian motion or some other alpha whole group integral. So in order to gain some intuition on this problem, let's look at a closely related sort of toy model of this problem. So I'm going to say that I have integrals that look like this. Okay, so I have some integrand function v that has some properties to it, and then I'm going to integrate against this. Let's call it as a rough path. And the key assumption that I'm going to make at the outset is that this rough path has order regularity greater than 30. Now I can do sort of a Taylor-like expansion of this integral. Okay, so if I make enough assumptions, then I can write down this integral as a Taylor expansion around the point xs in this fashion. So I have this first term that involves the increments of the process over this time interval. Okay, x1 st is just xt minus xs, that's okay. And then the second term is going to be the derivative of my integrand against a process x2, which is actually like this double integral. Okay, so key assumption in rough path theory is that these double integrals are actually well defined. Okay, this is not always going to be true. You can't always define these double integrals necessarily. And then if I look at the third term, as long as this double integral is well defined, then I can actually define this type of an integral in terms of what's known as a Young integral, provided these integrand functions, the derivatives of the integrand function, are nicely smooth. It has enough smoothness. So this is a key assumption. So building on this, toy example, okay, you can extend this to multiple dimensions. Okay, so you can consider an RD valued Hooker continuous path and define these these double integrals and what happens, and then define the solution of the integral. So to get to that, you can think of taking your Hooker continuous path and then doing a piecewise linearization. So in other words, in one dimension, it might look something like this. So if my linearized path will look something like this. Okay. And then my actual path is probably fluctuating. So look at xn, which is this linearization along some kind of a mesh. So in other words, these points are all 1 over n apart from each other. And consider this integral. Okay, so for any s and t, I will look at the nth order or the nth level integral, and this is well defined because this piecewise linear function is has sufficient regularity to it that you can define it in terms of a Riemann. Okay. The first rough path assumption will be that if x is a C alpha function with alpha greater than a third, then the process x to n will converge to some process x2 as n tends towards infinity. This is an assumption that we make. Now, in the case where x is Brownian motion, okay, so this is something that you've all probably seen in a class on stochastic calculus. If x is Brownian motion, then the limit x2 is actually can be written down as a trigonometry. It's provably the case. But for now, we're going to assume that some limit like this happens. There's some limiting variable. The second assumption is going to be that these vector fields, these integrand functions, they're going to be like nice, smooth and bounded. This is for simplicity. The theory, of course, is much more general. Okay, so the main theorem in Rothbard's theory, this is called as the universal limit theory. This is by Terry Banks. This shows that under these assumptions, that just to reiterate, you have this convergence and you have this bounded smoothness of these vector fields. If you define this function yn as the following integral, then this yn will converge to some function y, and this y can be seen as the integral part, as written over there. So integrated against our graph system. Okay, so it's under these assumptions. We are assuming that these, iterated integrals and so on exist, and then that lets us define the limit, and that limit can be interpreted as this. Okay, so to briefly summarize what Rothbard's theory does for us, you can take notions of these double integrals, triple integrals, possibly even more, okay, depending on the regularity of the paths of these driving systems, and then you take these smooth vector fields. And the theory lets you then define integrals of this form and solutions of differential equations. So rough differential equations and rough integrals are well defined through this theory. Okay. And the sort of remarkable thing about this theory is it works in considerable generality. Like this is a pathwise theory, right? Whereas Ito calculus is not a pathwise theory. And this becomes really important, particularly when you're doing control optimization and so on, where you want the solution map to your equation to be continuous. Whereas the Ito theory only tells you that the solution map is measured. That's insufficient when you're trying to do computation. You need continuity. And that's what Rothbard theory is. That's really the key takeaway from this part of the talk. Okay, so this lets us define these integrals. So we were interested in knowing what it means to integrate a term like that. But the story isn't done. Okay? Even though we know, what it means to define an integral like this, remember, I said that the value function had to be in C1 for it to satisfy this HJV equation. And you don't even need rough parts. Like you just take your ODE setting. The value function is actually never seen. In most cases, it is never seen. Okay, the value function actually typically looks something like, you might have a function with a kingdom. Okay, so it's going to be mostly smooth, but then there are going to be these points where it's just not differentiable. Okay, so it's not in C1, and this is what sort of spurred the development of what's called as a viscosity solution. Okay, and the key idea in viscosity solutions is to transfer derivatives onto test functions. Okay, we know that our solution is not differentiable everywhere. But can I sort of approximate it in some sense through a test function that has sufficient regularity to transfer the necessary derivatives on the test? So let me sort of try to illustrate that. Let's say that our value function looks something like this, and my test function at these points where I have these kinks will be like some smooth function that sort of bounds my value function from below and from above at these kinks. Okay, and I find test functions that sort of let me bound this. Now, why am I looking at these bounding functions from above and below? Okay. So the intuition behind viscosity solutions actually comes from thinking about the Bellman operator in discrete time. Okay. So let me just briefly take another slight detour. How much time do I have?
Well, 9 minutes.
9 minutes? Okay. I think that should be sufficient. So remember, in discrete time, the Bellman operator looks something like this. So if I have a function phi, so TV is going to look like say max control, have some reward plus the value function, the function phi of, let's say my dynamic involves some f, so I take f of x. Okay, and so this is the Bellman operator. And one well-known property of the Bellman operator is monotonicity. In other words, if phi of a function, phi of x, is less than or equal to the value function, v of x, this is true, let's say that this is true for all x, then the Bellman operator function, phi of x, this is going to be less than or equal to d of x, okay, for all x. And in fact, the value function is unique in the sense that it is the fixed point of the Bellman operator. Okay, so that's key. So the Bellman operator is sort of telling you that if I have a function that lower bounds my value function, then when I apply the Bellman operator, it's still lower bounds my value function. And that's sort of the intuition behind choosing functions that lower bound and upper bound your value function. Okay. And in the definition of the test function, as we see, this plays an important role. Okay, so the other sort of complication in our setting is that because we have this rough component in our HJB, then test functions also have to change. Okay, so the test functions have to become rough themselves. So we have to define a notion of a rough test function. And that's precisely what we do. So I won't try to read out this math to you. I'll just point out that this component here is sort of akin. It's exactly what you would find in the case with no rough component in the system dynamics. So you're just looking at the ODE setting, the dynamical system setting, then this is exactly what this would be the test function. And because we have this rough component, we get this rough integral as part of the definition of the test function. So therefore, this is a rough test function. Okay. Now, the definition of a viscosity solution is basically here. So we say that V, which is a rough viscosity, let's say, super solution of this equation, if for every test function psi, and we're looking at, so remember we had those points where we had kinks in them, right? So this was our value function. We had these kink points. Then so you can think of these as points where this V minus psi admits a local minimum. Then this psi st for this test function will be upper bounded by this by our Hamiltonian. But I really want to point out that you can rewrite this in a slightly different way. Right? So you can write it as psi p of y plus sup gamma and the Hamiltonian. Right? This is less than or equal to 0. But this less than or equal to 0 is literally the value function. Right? So the value function plus sup gamma h. Okay, so this you can sort of think of this as applying the Bellman operator on the test function, and this is applying the Bellman operator to the value function. So it's exactly the monotonicity property that's being reflected through these test functions. Okay, all right. So all of that is to say, using these test functions and this notion of a viscosity super solution and sub-solution, you just flip the inequalities, you get a sub-solution. We can show that the value function V, which is this guy here, okay, looking at the sup over all possible controls of this pathwise objective, this value function V is the unique rough viscosity solution to this equation. Okay, so this is like a full characterization of the value function to the dynamic programming principle, and we understand what this value function is. It's rough setting. Okay, so this is the key result, the main theorem in the paper. But let me sort of conclude. Well, I mean, I'm not going to present the proof; it's too technical. But I'll just point out that use some ideas from rough flows, which then let us convert this rough PDE into a deterministic PDE, and then we get the uniqueness of the viscosity solution to this new deterministic PDE. Okay, I want to tie this back to where this whole conversation started, with exploration involving Gibbs distribution. Okay. So going back to the Brownian motion set. Okay, so I'm going to assume that I have Brownian motion driving my equation now, but with exploratory dynamics. Now, if the model is fully known, of course, I don't need to explore, and so I can assume that these gammas are Dirac measures. But really, I don't want it to be a Dirac measure. I want it to have some kind of spread to it. Right? So the entropy should be higher, and so I'm going to introduce a differential entropy term into my cost function. Okay, so this is called as entropy regularized reinforcement. And there is a version of this for continuous time that was introduced in this recent paper by Wang, Natalia, Zaripoglu, and Shin Zhu, where they looked at a cost function that looks like this. Okay, so you have your usual running cost, but then you also have this regularizer involving the differential entropy. And in our setting, we want to use a similar objective, okay? But not with Brownian motion, but driven by a rough path. Okay? It could be fractional Brownian motion, whatever, but it's a rough path. And we're doing this pathwise optimization. And it turns out that if I look at the Hamiltonian for my HAB, then I can show using the so-called Wronska-Walden free energy or variation principle that the Gibbs distribution, the optimal exploration strategy in this case, when you're driven by a rough path in this continuous time setting, has this form. Okay, at this point, that there's explicit dependence on the path roughness, just as you asked. Because this gradient of the value function explicitly depends on the driving signal. Okay. And this turns out to be the optimal exploration strategy.
What is lambda? It's just another.
Yeah, so lambda is the sort of that temperature term, but it turns out to be this regularization. Coefficient. Okay. Yeah, as I noted, gamma star is path dependent. And one issue here, of course, is that this gradient of V may not actually exist. So you have to define this through some sort of notion of a generalized differential or a general superset. Okay, so let me conclude by giving you some final thoughts. The main, I started by saying that we want to solve this RL eventually, right? And in RL, you actually want to resolve the expectation. Right? There's uncertainty in the path. And I want a policy that works a priori without knowing what the path is. What I've done so far is I've said, give me the path, I'll tell you what. It's not good. Well, so the problem I really want to solve is this one, right? So I want to extend what I've done to these expected cost objectives. It unfortunately turns out to be really, really hard to do it. Move from this pathwise setting to this expectation setting is really hard. There are some ideas that have been used, sort of based on these insights from Rogers, LCG Rogers, and Davis and Burstein, I think, as well, had sort of similar ideas. This is called as a pure dual method. Essentially, what you do is you introduce this martingale process, Z, that sort of lets you compensate for the following, right? So what we want to do is maximize this expectation. And what we have done so far is we know how to do this. Right? So I can do max over gamma of this objective. Okay? This I know. I can solve this pathwise, and then I can take an average of it. But this is necessarily greater than or equal to this this V of S Y. This. And it's necessarily better than that because I'm optimizing pathways and then average. So I need to, tighten this inequality somehow. And the way you can tighten it is by introducing a sort of martingale process and then optimizing over the possible martingale processes. Unfortunately, this idea of using these sort of pure dual methods and these compensating martingales only works when the driving signal is Brownian motion and it's rough. Okay. It doesn't even work for fractional Brownian motion. So some idea is required. So this is like a frontier, like for this problem. But let me end there. And here's some contact information. Thank you for your attention. And I just want to point out that I'm always looking for students, looking to hire 1 to 2 graduate students. So if anyone is interested, please reach out. Here's my contact information. Thank you.
Thanks a lot, Professor. for a very interesting talk. So audience, please feel free to ask any questions.
Why is 1/3 the older continuity crucial in the part theory?
It is not crucial. It helps for me to talk about rough paths in this talk because then I only have to introduce one double integral. If I have more than that, if I have worse regularity than a third, let's say less than a third, then you're really looking at multiple iterated. The number of iterated integrals you require to define the rough path is inversely related to the order coefficient. Okay, so the smaller that is, the more the rough components. But it's not,
So rough path theory is also for Brownian motion as well. Because
Yes.
half is greater than 1.
you can definitely talk about. So, for example, in this paper by D, so they look at control when you're driven by Brownian motion, but you're rough lifted. Okay, so you can do like pathways.
So you do power and then you go to expectation by the effect.
So, I mean, their theory actually is looking at rough paths in general, but this main result, where they're sort of looking at stochastic control, that is purely for Brownian motion. So they're looking at Brownian motion, that's rough lifting. They're looking at like a rough version of Brownian motion, and then they're sort of doing this compensation.
This is motivation for entropy.
Yeah, so the idea behind entropy regularization is to, let's look at this situation. So I have this control problem. Let's suppose that I didn't have this entropy term, right? So this is like the standard control. This entropy term will, encourage your optimization problem, finding the sort of randomizing policies that are not degenerate. Okay. So it's possible that without this term, the optimal solution to your problem is actually like a degenerate measure. In other words, it's just like a function. So by introducing this term, you're sort of penalizing those types, which is sort of what you want. Right? If you want to do exploration, you want your optimal exploration measures to not be degenerate. You don't want them to be Dirac. Instead, you want them to have some spread. That's the motivation. So this is sort of like exactly mirroring, what people do in discrete time reinforcement learning. Something called as maximum entropy. It's usually written as max ent. So it exactly mirrors that.
So entropy sort of measure of randomness, like that sort of says like some kind of exploration is what we are planning.
Exactly.
And but in the end, your goal was really reward, right? So
Eventually.
yeah, so you really care about the integral. Add this extra exploration term as well.
Yeah. I think eventually what you want to push that lambda down to 0.
Okay.
So there's still like this question of how do I exploit? I only said how to exploit. Exploitation would involve like scheduling that lambda down to 0 in some way. So that you initially explore a lot, you learn a lot, and then you start exploiting more. So I think that's the whole RL part, which is why the title has 2 words. This is my call.
We have arranged the refreshments at coffee, right? So please feel free to continue your discussions at the coffee. Thank you everyone and have a great evening. And by the way, one small reminder for the tomorrow's talk. So tomorrow, Professor Tinghi from Penn State University is going to speak on CT scan for networks. The talk will be at GJH from 5 p.m. to 6 p.m. So please feel free to attend tomorrow. Thank you.